This video is about problem 4.7. So let's take a look. Okay, so a trapjaw ant found throughout the tropical South America catches its prey by very rapidly closing its mandibles around its victims, shown in figure 1. Uh, figure 1 shows the speed of one of the mandible jaws versus time in microseconds. Okay, so let's take a look at the figure here. Okay, and with this problem, it's really important to remember, okay, that it's in microseconds, not seconds, because I'll tell you, when I did this problem the first time, I did it in seconds and I got the wrong answer. I was like, what the heck, man? It doesn't make any sense. And then I was like, oh, I looked at the axis and I was like, oh, that's in microseconds, not seconds. Okay. So that's important to remember. Now, our problem here asks, okay, it says, what is the magnitude of the maximum acceleration of the ant's mandibles? Okay, so that means that we need to find basically the steepest slope on the graph, and that's going to be our acceleration. Okay, so I'm looking at the graph here, and okay, I have this part here. Let me draw something. I'm going to annotate my graph here. Okay, um, this part right here with this dot, and then with this dot. Okay, I made those purple marks there, so I'll put a big X. Okay, right there, and I'll put another X right there. Okay. To me, that looks like the steepest part of the plot. And so I'm going to calculate the slope right there. Okay, I'm going to grab a line here. Okay, and I'm going to say, what is my slope of my graph? Okay, so let's figure out, we need to get the acceleration from this plot. Okay, because remember, we have a velocity versus time plot. And if we want to find our acceleration, then we need to find the slope of our velocity versus time graph, and that's going to tell us what the acceleration is. Okay, so let's switch here, and I'll get ready big enough so that you can see it. I don't not have the shadow in the picture. Perfect. Okay, so first of all, um, we're going to write down that the acceleration is equal to delta V over delta T. Okay, and that's going to be VF minus VI. Okay, and that's really important. You do VF minus VI, and then we're going to have TF minus TI here. Okay, and um, I can look at my plot over here, and I can say right there that my first point is, it looks like we have so my x-axis is time, and that's going to be 40 microseconds. Okay, now if you don't recall, 40 microseconds means it means 40 times 10 to the minus 6 seconds. That's a microsecond. Okay, so the microseconds there means times 10 to the 6. Okay, that's fine. So my first point is going to be 40 microseconds. And then I look over here, my velocity, and that's about 5 meters per second. Okay, so this is going to be our point here. So I'm going to write this down. 40 microseconds. This is 0.1, and my velocity is 5 meters per second. Okay, and that is my that's my initial, yeah, that's my initial velocity and my initial time. Okay, so we've got VI here and TI here. Okay, and then I'm going to look up at this point here. Hey, yeah, I did that correctly. Okay, so my final time and my final velocity, so I'm going to have VF over here. I'm going to write that over there. V final is 40 meters per second. Okay, and then the time there is 60. Oh shoot, no, I'm getting confused here. Okay, so I want to do my velocity. You know what? It's supposed to be X and then Y. That's why I'm getting messed up here. I'm going to cross that out once. Okay, so my actual points should be the time. Wait, I did it right. No, it's time and then velocity. Oh, see, okay. 40 microseconds and then 5 meters per second. That's point one. Okay, point two is going to be our, yes, the time. We're going to do that first. That's going to be 60 microseconds. And then our velocity at that point there, I'm reading this off the graph, that is 40 meters per second. Okay, so this is, yeah, right here, this is our final velocity. This is our final time. And then this is our initial velocity and our initial time. Okay, so now we can calculate our acceleration here. We can calculate our acceleration here. And our acceleration is going to equal VF minus VI divided by TF minus TI. I've got the final time and velocity first. So now I'm going to plug in my numbers here. Okay, so what do we have? Our final velocity is 40 meters per second minus 5 meters per second. Okay, that's on that's the numerator there. Okay, I'll stop sharing so we can make this bigger. There we go. All right. I've got all my I read the plot. I don't need to look at it right now. Okay, so my final time that goes first. So this is 60 microseconds minus 40 microseconds. Okay. All right, so I'm gonna do this algebra now. Okay, this will be 35 meters per second. So 40 minus 5 is 35 meters per second. Down the bottom, 60 minus 40, that's going to give me 20 microseconds. Okay? And so now I'm gonna actually write this out. So this is 35 meters per second divided by 20 times 10 to the minus 6 seconds. I don't want to forget that when I plug it into my calculator because that will give you the wrong answer. All right, so let's get MATLAB out here. I choose you, MATLAB. All right, so we have down here, we're going to have 35 divided by, I'm going to put a bracket there, so that's 20 times 10, okay, to the minus 6, okay, and that is going to give me, that looks about right. Okay, so what do I got there? All right, I have 1.75 times 10 to the 6. Okay, so 6 meters per second squared. Okay, so and I do end up with the right units because see, here I have meters per second. So let me write it over here so it's a little bit more clear about what I'm talking about. So in the denominator, I have 20 times 10 to the minus 6 seconds. Okay, so I have seconds there. And then that's all in the denominator. And over here for my velocity, I have meters per second. Okay, so this I'm just multiplying here. So see in my denominator, I get seconds squared. And so this is my velocity here. Okay. And I recall that in the plot, I only have two significant digits, right? Each one only has two significant digits. So I'm going to round this off to 1.8 times 10 to the 6 meters per second squared. And that is really fast. To give you some kind of reference here, I remember that a really fast sports car like a Corvette actually has an acceleration of 9.6 meters per second squared. I had a friend who had a 1969 Dodge Charger. He probably had an acceleration like this, and it was amazing because as you drove around in this huge 1960s muscle car, you could see the gas gauge moving down. It got like 1 mile per gallon, maybe two. I'm generous. All right. Let's go back to the problem and let's plug in our number here and see what we got. Just check out our value. Okay, this is going to be 1.8, 1.8, and then we want, what do we want? Symbols. I'm not sure how to use the symbols, man, so I'm just going to do times 10 to 6, okay? And this is meters per second, and we're gonna do squared. There it is. Boom. Did we get it? Let's get it correct. All right, we did it. We got it correct. It could have been 1.85. They maybe read the graph a little bit differently than me, but it's close enough. All right. The mass of a trap-jaw ant's mandible has been estimated to be about 1.5 times 10 to the 7th kilograms. Estimate the maximum force exerted by one mandible. All right, well, good thing we know about Newton's second law. This is part B. Okay, I'm going to write down my equation. It's a big one here. The muy importante. F equals m times a. There it is. All right, we know the acceleration. We just calculated this thing, okay? Now, uh, what does it tell us in this problem? Okay, it tells us the mass of the ant's mandibles, which it can't be a lot. Okay, so yes, the acceleration is very high, but our mass is pretty small. Okay, so 1.5 times 10 to the minus 7 kilograms. Okay, so now we can plug in our numbers here. Okay, and we're gonna get our answer. Okay, that wasn't bad. And this kind of problem, I could see this being on the exam. Okay, you find the acceleration, then find the force. F equals ma. Boom. All right, let's plug in the numbers here. So we have 1.5 times 10 to the minus 7 kilograms, then times 9.6 meters per second squared. All right, let's throw it in MATLAB. Throw it in MATLAB. Get a calculator. Hopefully you have a calculator with like a screen on it so you can put in a bunch of equations and you can see what you're doing. So this is, oh, we didn't put the exponential sign there. That is not good. All right. So then we got times 9.6 and we get, okay, that gives us a force. Okay, so it's quite a bit less than 1 Newton. Okay, that's a force of 1.44 times 10 to the minus 6 newtons. Okay, and that's 1.44, so we're gonna round that down. So it's just gonna be 1.4 times 10 to the minus 6 newtons. All right, let's throw in the answer. Here we go. Okay, we're gonna do 1.4 times 10 to the minus 6. And then we're gonna do newtons. Incorrect. Incorrect. Okay, could it be 1.44? What did we do wrong? What has gone wrong? Okay, what is it asking for? Estimate the maximum force exerted by one mandible. Okay, the mass of a trapjaw ant's mandible has an estimated. Okay, so we have our mass. Did we plug it into MATLAB correctly? Ooh, that looks okay. Wait a minute. Wait, for my acceleration, what have I what have I done here? What is going on? Oh my gosh. Do you see what I did here? Look at this. I put in the acceleration of the Corvette. What the heck am I doing here, Dr. Wisby? Oh my, no, no, that's wrong. I was like, why does it, okay, no. Okay, we're gonna read it. This is why you get multiple tries on the exam because let's face it, man, sometimes you're gonna make mistakes. Everybody makes mistakes, okay? It's part of life. Okay, this is wrong. This is wrong. Wow. Okay, well I understand now why I was like that doesn't seem like a lot of force. 1.5 times 10 to the minus 6 newtons? I mean, there's more force if you exhale through your nose. Yeah, wow, that's okay. Well, we're gonna put in the right numbers now. Okay, so 1.8. Yeah, we have 1.85. I think that was the actual. Well, we have no. We'll do 1.8. That's what we went with in our answer. Times 10 to the 6. Oh, and we need the exponential sign there. Okay. Oh, okay. Now that's 0.27 newtons. Oh, wow. Well, okay, we got it. We did this problem. And let me just say, okay, if you ever make a mistake and you did the problem correctly, and let's say you put in the acceleration of a 1969 Dodge Charger instead of the acceleration of the ant's mandible, uh, I'm not going to hold that against you. So basically, show your work. And if I see, I was like, oh man, why did you put that acceleration there? I'm not going to take off a lot of points. Okay, so as you can see, mistakes happen, but we fixed our mistake and we had the right answer in the end. Thank you for watching this video. There will be more videos that follow, but thanks for watching. Like and
Thank you, like and subscribe down below.
thanks.